first science seminar. I'm Chris Newhouse, biology professor. My privilege today to introduce the speaker for the day, Dr. Baldwin. Dr. Baldwin did his undergraduate degree at one of our sister schools, George Fox University in Oregon. He did graduate work at University of New Mexico.
Yay! Go Lobos! Go Lobos!
After that, he traveled to Japan for a postdoctoral study where an unexpected blessing occurred. He met his wife.
Yay!
And then, even better for us, he came to Spring Arbor University. Dr. Baldwin is unique among organic chemists. Some of you have peers at other institutions and could probably verify it there. But at many other schools, organic chemistry is seen as the make or break class, the one where you're weeded out, the one where the professor shows you how ignorant you really are and that you really don't belong in medicine, graduate school, or maybe not even life. But Dr. Baldwin has his goal, success. And he wants every one of his students to learn organic chemistry. Obviously, it's very important for us, but that he's not trying to eliminate people. He's trying to get everyone up to a level of understanding and learning. And I'm incredibly thankful to work at an institution where that is the organic chemistry ethos, rather than to show your ignorance. I mean, all of us understand that we've got some ignorance, but it's his goal to make sure that we take care of that and succeed despite that. So, Dr. Baldwin, welcome, and eager to hear what you're telling us.
Good. All right, let's do this. So, this is going to be talking about the development of the soap recipe that I call Macadacoconutmeg Soap. Now, you notice that there was no hip movement. If you were waiting for that, it's not going to happen today, all right? But maybe another time you can ask me to do it. And that's as close as I'll ever get to a dance, all right? Jamie and Tala. Anyway, so this is what we're going to do. The things that I'm going to talk about are the greenification of this process. Everybody can make soap. Even in high school, you often have soap recipes. But here at Spring Arbor, because we're a Christian liberal arts school, we want to do things that are in response to God's stated purpose for humans as being stewards of our environment. And if you do things in a green way, you do it so that it's better for the environment. You don't start out with super, super dangerous things and make super, super dangerous products. And you try to do the process of conversion to whatever you want to have as your outcome in a way that is sensitive to the environment and doesn't, like, grossification of the environment. You don't want that to be something that happens in your push to make money or to teach people how to do stuff. You want to be sensitive. So, this was developed by myself and lots and lots of student input. One of the things that really drives me to be at Spring Arbor is that I can do research through your hands. I very rarely will go into the lab just by myself and do an experiment. I think of the experiment, usually while I'm taking a shower. That's weird. You get great thoughts in the shower. But anyway, something about it. And I try to make those thoughts become reality through your hands. That requires that I train you in a lot of techniques, and I do this patience thing, and it takes time, and it takes investment, and it breaks my heart every time someone graduates, because then I get to start it all over again. But that's part of being an undergraduate professor who wants to teach people how to do this thing called science. And my particular area of science is synthetic organic chemistry. So, That's what this is going to be about. Saponification is the fancy pants term that chemists use for taking a triglyceride molecule, code name for fats or oils, and snipping the arms off of that molecule. There are 3 arms. We usually have 2, right? Most of us in this room have 2 arms. We're not like insects or anything like that. So, but triglycerides are different. They have 3 arms. We want to chemically snip each of those arms off because we want to make the lower molecules, which are called soap, and we also want to do it with the chemical scissors called sodium hydroxide. So that's the process. But what is it about these 3 arms that you see nutrition labels about? Because if the things I talk about in terms of chemistry have nothing to do with your everyday life or anything that you can relate to, then I'm probably not, I'm going to miss out certainly on an opportunity to connect with you, the student. So what I notice when I pick up a bottle of peanut oil or even peanut butter is you look on the back and you can read all these weird words. Some of those words go something like saturated and unsaturated and polyunsaturated. If I'm unable to teach you what those terms mean in terms of the chemical structure, then I have failed as a chemist, because chemists are absolutely convinced that our verbiage and our picture of the world as a model have to match up, and we also think there is great power in doing that. So, the connection is this. See that red arm? It's like that triglyceride has 3 different arms, right? This is not necessarily the case for every molecule that you find in a container of peanut butter, but this is a gross misrepresentation that's trying to cover a lot of ground. So let's pretend that one of the arms is what we call a straight chain. It has only carbon-to-carbon single bond connections. That type of arm contributes to the saturation factor in fats and oils. And it also tends to make things a solid at room temperature. So when you see saturated, that's chemically what we're talking about. Now the other arm, it's a little bit not so easy to see, but the other arm has 1 carbon-to-carbon double bond. And if you look carefully at it, it has a certain shape. It has kind of a cup shape to that carbon-carbon double bond connection. That's because not only is it not as saturated as it could be with hydrogen, that's why it's called unsaturated. It's unsaturated, but it's also unsaturated in a certain way, and we have a term for that. We call that a cis double bond. Cis double bonds are favored in biochemistry. See, this is how I relate things in organic chemistry to those of you who are bound to be a doctor or a physician's assistant or something else, because I don't want you to be bored in my class, right? I throw those things out once in a while. Cis double bonds are often found in natural products. They are an energy storage molecular portion. So that cis double bond is what's found in most natural materials. Also, you see the term polyunsaturated. Look at that. And that just means that there's more than 1 site of unsaturation. See how these words are not really that mysterious? Poly just means many. So polyunsaturated means, yeah, look at that. There's more than 1 cis double bond in that structure. And that's what you often see in things like lanolin, an oil that comes from the fur of a sheep. Those are polyunsaturated fats by and large. So you've got all these different triglycerides with the 3 arms. And what you do in the process of saponification is you use sodium hydroxide chemical scissors, and you snip those arms off. Now the molecule doesn't scream in pain, it's not alive, right? And so that's okay, you haven't hurt anybody. That makes 2 different kinds of products. One is the molecule glycerol. You can see in black that in the original fat, the stuff was there that becomes glycerol, but when those 3 carbons are in the original triglyceride, we don't call it glycerin or glycerol. We call it, it's part of the triglyceride, right? And that's part of chemistry, realizing that chemicals and their original form can be different. and it's something that sometimes gets all mixed together and goofed up if all you do is read on the internet, because they talk about glycerin soaps. What in the world is a glycerin soap, or a soap that contains glycerol? Well, it's actually nothing special. Every time you make soap, you have to make glycerin as a side product. So every soap, no matter whether you buy it at Bath and Body Works, and they spend a lot of money on advertising to say that we make glycerol soaps or glycerin soaps, or you go upstairs and you make soap with me, you're making a glycerin soap because that's how the process works. There's nothing special about Bath and Body Works. Now, that's not quite true. Bath and Body Works actually pumps up their recipe with glycerol, okay, just like Arnold. And that does actually change the formula of the soap. If you add more glycerin to your soap recipe, you can actually make that jewel-like character that is real well known in Bath and Body Works especially. It makes a pretty soap. It also takes a lot of processing that they can get away with doing because they have like huge vats of it and lots of money to spend on infrastructure. We don't have that here, right? This is SAU. So we got to do things easy and simple. More like you would do it in your kitchen, right? If you were a home soap maker. So glycerol is one of them. The other thing that you make is the actual soap. Now soap has two major parts. One part is called the fatty acid residue, and that has always a long carbon-to-carbon chain. So that's what's in red, blue, and green. And it doesn't matter what's in there, that's called the alkyl chain portion of the soap molecule. Then at the end, you've got this carbon double bond oxygen, single bond to oxygen with a negative charge. That group at the end is called a carboxylate group, as opposed to a carboxylic acid group. The difference between those two is if you take away a proton from an H from a carboxylic acid, you make a carboxylate. In soap, it's always a carboxylate, negatively charged. It's going to be important. And paired with that negative charge, because you always have to have pairs. You never get to have just pure negative charges unless you're in the center of a bomb or something like that. Then that negative charge has to be paired off with a plus charge, just like when you get married, you know, you have to have an opposite, right? And it works best that way. Marrying exactly the same personality doesn't usually work out so great. You got to be complementary. In the same way, soap is complementary. The negativeness, hear this analogy, the negativeness of the carboxylate is perfectly balanced by the ladylike plusness of the cation. Doesn't that work? I could be a marriage counselor right here. No one pays me money for that, but I could. All right, so that's the overview of soap. Now let's back up a little bit to talk about fats and oils, because remember, this is something that you're likely to see in the grocery store. What in the world is a saturated fat? You may have heard that saturated fats are not so good for your arteries, right? You tend to die quicker because you have clogs, plaques, and such. And so no one wants to eat saturated fat. That's bad for you, right? Well, remember, we're not talking about eating the soap products, right? You know, the only time that happens is when you said some words that mom didn't think were supposed to come out of your nice little mouth, right? So unless you're in the habit of washing your mouth out with soap, who does that intentionally, then saturated shouldn't be too much of a problem. In soap making, saturated fats are solids at room temperature, and they tend to contribute to the soap product that is also going to be nice and firm and solid when you're done with it. And it also usually gives a nice lather. So those are characteristics that you get from saturated fats. Coconut oil is an excellent example of a saturated fat. It just has all carbon-to-carbon single bonds. So as a chemist, I always think about a word, and then what does it mean in terms of chemical structure? So I'm always going to come back to that. Unsaturated fats are fats that contain at least one carbon-to-carbon double bond. They could have more than one, but they always have to have at least one carbon-to-carbon double bond. And that means that each of those arms has a kink in it. That kink in the chemical structure determines whether or not the oil is a liquid or a solid at room temperature. If it's got some unsaturation in the arms, it's going to be a liquid at room temperature. And most of the oils that we get from temperate climate seeds are liquids at room temperature. It's just the way that biology is programmed by the Lord, right? So, things like olive oil are monounsaturated fats. They're really good for soap making because they give emollients to the soap. That means that they help to trap a water layer between the outside of your skin and the yucky environment that you encounter every time you shake someone's hand who just had a cold and snoozled all over their hand, right? So a little bit of protection there. That could be a good thing. Now, trans-unsaturated fats. How many of you have heard of that term, trans-unsaturated? Is that good or bad for your health? It's bad because, now this, you have to be really careful. This is, as I understand it, correlated to heart disease. We don't know for sure that trans-unsaturated fats, which are basically made during an artificial process called partial hydrogenation. You see partially hydrogenated fats on your peanut butter, then you know that there's probably some trans-unsaturated fats in the product that you're eating with your peanut butter and jelly sandwich. Now, that might cause more plaques in your arteries, and it might not be so good for you, right? But unless, again, you're washing your mouth out with soap, I don't know why you do that, but unless you're doing that, you're not going to ingest the trans-unsaturated fats that are present in such a type of fat. And so for soap making, trans-unsaturated fats are a non-issue. You don't have to worry about it. So you could use that partially hydrogenated container of cooking oil to make soap out of it. It'd be just fine health-wise for you. It'd be on the surface of your skin, not inside your body in your bloodstream. So, might have heard of trans-unsaturated fats. It's a problem in dietary requirements, but not a problem for soap making. Now, let's talk about the chemical identity of this thing that we call soap. Soap is an amphiphilic molecule. That means that on one end of the molecule, there is a hydrophilic group. That's the groups in blue. Those are all carboxylate anions. They have a -1 charge. Now, being an organic chemist, I don't really care too much about what has to hang around the minus charge to cancel it out. So, because it's not anything to do with carbon, and you know I'm Dr. Carbon, right? So I'm leaving it off. In your mind, you probably should make the adjustment that those negative charges are always canceled out by a plus charge. But for now, I'm trying to emphasize the soap molecule and not the counterion. I'll get to the counterion in the next frame. So that carboxylate anion is hydrophilic. It loves water. That means that this two-ended molecule tends to arrange itself in water so that the surface of the molecule thing is similar to the water environment. It has to be polar. That means that this whole thing, this whole group of molecules called a micelle, tends to be water soluble. We're going to come back to that. It's very important. Now, the other end of the individual molecule is this alkyl chain. It's got a lot of carbon and hydrogen. Carbons and hydrogen are what you normally see in petroleum. Does oil mix with water? No. In fact, oil and water is the basis of a vinaigrette salad dressing. And if you know what happens if you don't shake the oil and vinegar salad dressing right, you get grease coming out on your salad, and that's not as good as mixing in the nice tanginess of vinegar. So, and we'll get back to that in just a minute too. So, back to the micelles. you have to have these two oppositely character-ended molecules in order to program or design the formation of micelles. Why is a micelle so important? A micelle is critical because soap is usually used to clean things, right? Whether it's your clothes that have dirt particles trapped in the warp and woof of the material, or your body, which has a lot of crevices. I'm a little older than you all, so I have more crinkles in my skin, right? Most of us do as we age. So that's going to trap more dirt, right? So I got to get the dirt away from my clothes or from my body. Micelles are the perfect answer to that because the interior of this packet that we call a micelle loves dirt. It loves things that are the opposite character of water. So the outside of the sphere of a collection of soap molecules loves water. The whole package loves water, but the interior of the package hates water. In fact, it loves dirt. So all the dirt gets absorbed into the center of the transport molecule or assembly called a micelle, and that means that the dirt gets taken out of your clothes or out of the crevices and encapsulated in the transport molecule or transport assembly called a micelle, and then it goes away in the drain water, and you come out refreshed and smelling like a rose rather than all gross and sticky from your workout, or your clothes, instead of being gray, will now be the color they're supposed to be, which usually is white, but some other nice colors too. So that's how soap cleans. Now, let's backtrack a little bit more and talk about the cation choice, because remember, every soap molecule, whether I want this to be important or not, is made up of carbon-containing stuff. That's the amphiphilic part of the soap, the one that has the carboxylate on one end and the tail, or the hydrophobic alkyl portion on the other end. But also, there's that cation thing. If we look over at the periodic chart, where God wrote the rules for how chemistry is going to work into the fabric that a Russian came up with, by the way, so we're mixing all kinds of metaphors here. But if you look at the periodic chart and you find sodium, for some of you, you're looking frantically for SO, but those of you who know a little bit know that Na is the elemental symbol for sodium, so I'll make that easier for you to find. Sodium is number 11 on the chart. The important thing to notice is that it's in the first column of the periodic chart. That's called the alkali metal family. So chemists love to do substitutions because we've learned that if we substitute one thing for another similar thing, we can get a completely different new combination. And we call that synthesis. And we make things. We build things from the elements, the elemental foundational principles of chemistry, and we can make new things that you don't even know what to use them for. That's the power of synthetic chemistry. We can invent the future, which is really kind of fun to think about. Okay, so back to this. Sodium cation paired soaps make the commercial soap that you would use to wash your hands or wash your face, or even do your laundry. If you replace the sodium +1 with the lithium +1, you make special types of lubricants. And I haven't been able to find out specific examples of lithium salts, but I know they're made. And that was one of the things I looked around for and I couldn't find. So if anybody knows in the question and answer period, what's lithium salt?
White grease.
White grease, there we go. Thank you. I've heard that before, but I couldn't find the example. So, thank you, Dr. Wyman. So, lithium salts are usually made for lubricants, specialty lubricants. So if you do that substitution, you can make a different kind of material. Being a chemist, we look in the same family for another type of material solution. And if you go down a little bit further, you come to potassium, K. If you substitute potassium for sodium, you tend to make liquid soaps. Now you can just put it in a pump and you can get out the foam, right? You've all seen those. Those are new things. We've known about potassium soap for a long time. It's nothing really that new. And it chemically just comes down to a simple substitution. Then if you move over one family to the alkaline earths that start with beryllium and go down to radium, then you have a series of things to choose from which are 2+ charged. And 2+ charged is going to be able to marry 2 anions to it, right? So you're making a still different material. That can be good or bad. It can be good if the countercation is barium and you make a salt from barium hydroxide, or a soap from barium hydroxide that gives a barium dicarboxylate, and that's good for lubricants on drill heads. That's how you can get water from your well or oil from the ground. You got to be able to lubricate that drill head, otherwise it breaks. That's no fun. But it's a problem if the counterion is calcium, magnesium, or even iron. That's when you get ring around bathtub. So not all of these solutions, that's a pun, solutions. It's always a mixture, it's dissolving water, it's a solution. Not all of these solutions are good. Insoluble curds are a problem. We solve that problem with water softeners, which basically takes out the 2+ ions and replaces them with sodium. Why? Because sodium carboxylates are soluble in water, so the dirt goes into the micelles and goes away from you. So that's kind of the chemistry behind all of that cation choice. This is Melissa McClish. She made some really nice soap, and I just thought it was a good picture. All right. So that's the background on soap. What have we done here at Spring Arbor to develop greener choices for making soap? Well, one of the things that Jesse Kramer, who graduated in 2012, helped me with was trying to figure out if there's an alternative trace contributing fat that we can find. I figured out by chance that nutmeg has trace producing molecules in it. I don't know what those molecules are. I think they're brown in color, and I think they're also responsible for the nice scent of nutmeg. But it turns out to help the soap change from a watery consistency. No one wants to wash their hands in just pure sludge, right? You want to have a firm bar, usually, unless you are purposefully making liquid soap. And the nutmeg powder helps the soap recipe to go from watery consistency to whipped cream consistency. As you stir the recipe every time you're making a soap, it goes through this process. That trace can be quick, which it is in the presence of nutmeg, or it can be an hour and a half of manual stirring. Which do you vote for in lab? Right, I want to stir for an hour and a half and talk about things that don't have anything to do with chemistry. Yeah, I know how that goes, people. There's too much boyfriend-girlfriend talk in lab if I have you stir manually for an hour and a half. So to cut down on that, I discovered that nutmeg is the answer. 5 minutes doesn't give you enough time to get off on those side subjects that I'm trying to avoid during lab. Okay, so what she did was she thought, oh, let's look at other cultures in the world and think about how they might have solved this similar problem, because South Pacific Islanders had to have some kind of soap product in their lives, and they had coconuts available to them, but there are no agents in coconut that help the trace to happen quickly. So what else might it have been? We don't know what it was. We don't even know if this was a real issue for islanders, but what if kukui nuts, which are normally, their shells are used to make leis, if you've ever been to Hawaii, there's a nut inside those that can be used to make candles, and they can also be used as a soap oil source. She did the same thing with kukui nuts that we do with nutmeg powder, and guess what? It didn't work. Yeah, we wanted the answer to be, oh, we found something that no one else knows about. Yeah. She helped us accumulate sufficient failure. And that is a very important thing to remember about all research, especially scientific research. Not every time do you hit a home run. Sometimes it's a grounder, right, Alika? And sometimes the pitcher is right in your face and catches it as it leaves your bat, because you're hitting it like I would. okay? And it's really, really pathetic, and it's easy to pick me off. So that was one of those cases. So what Jessie found out was you don't use kukui nuts to substitute for nutmeg powder. Well, she was a good student, so she tried something else. She thought, well, how did Native Americans in the US get a quicker trace on their soap? Because they had to wash themselves. Maybe they used pine needles, because pine needles are kind of sticky sometimes at certain times in the lifetime of the plant. So maybe that pitch has something to do with helping a trace to develop. I don't know. Couldn't find anything about it in the literature. It's worth trying. So she did that, and no, you kind of guessed it. Didn't give a faster trace, but it gave a beautiful green color because of the chlorophyll that's in the pine needles. So it made a greener soap. Huh? So she didn't completely fail. She certainly accumulated a lot of sufficient failure, but she succeeded in terms of making a green soap. So that's a story with a great ending to it. Now, other people have done other things. One of the challenges we have in really making this process green is how far back do you want to go in the process to get the original stuff and not use electricity to get it, right? So we kind of made a compromise in terms of the coconut oil. I just accept that we're going to buy that from Walmart. But with the seed oil, the liquid oil component of the recipe, it turns out that you can get a home hand-cranked press for about $150. So you could actually do this at your house if you wanted oil for an oil and vinegar salad dressing. And we use it to produce enough liquid emollient-causing oil for our recipes. And it works really well. As you can see, Nathan has been cloned and split into two attractive parts, as opposed to Nathan, who's kind of like a guy. Yeah. Anyway, these are much nicer models for operation of the crank. This is Amber and Grace, by the way. And they agreed to pose making some almond oil. They're pretending, really. But you can see the tension in Grace's forearm, right? So he's like hulked out, right? And Nathan had to hulk out to make the oil from it. Once you grind it and you have to heat it with a candle, it's not so easy to see that. You can see the burn marks on the close-up. That is liquid oil coming off, coming out of the machine that is just pressed from the natural nuts. So Nathan really helped us develop this experiment so that we used person power instead of electricity to obtain the emollient portion of the soap recipe. And for that, we thank him very much. He sweat a lot. So, finally, to Macadacoconutmeg Soap. How do we make it? Well, you have three different oil components. The first component is the macadamia nut oil. We get that from Australia. You can actually press it in the Pitaba press. If you get macadamia nuts, they're very expensive. I don't usually do that. I've discovered that sunflower seeds work a lot better, and they're significantly cheaper. They also come from a temperate climate instead of from an exotic environment, so that's another reason they're cheaper. But for my showcase formula, that's what I use, the macadamia nut oil. That gives emollients to the soap product. Then the coconut oil gives you a nice lather. It also comes from the tropics. It sounds really exotic, right? And that's kind of what I was going for. And then the nutmeg butter, remember, that's the thing that causes the trace. Because who wants to hand stir for an hour and a half? You don't have time for that. You could get a lot of angry birds in that time, right? So we have nutmeg butter, and those are all tropical sourced things. So these soaps, you could probably sell them for $100 a bar, right? Maybe. So here's the process. I actually put this up on Blackboard last year so that students could see the step-by-step process that I had developed and that I wanted them to replicate. So you start out weighing the nutmeg into a syringe barrel. Just put the powder in there. Make sure that there's a piece of cotton in the bottom or a piece of cheesecloth. That works really, really well. And then you pour the macadamia nut oil or the coconut oil on top of that. Just pour it on top. You don't have to mix anything. Just pour it on top. Then you take that whole thing, lean it inside a beaker, and stick it in the microwave and turn it on, and that will heat up the oil to at least 65 degrees. I found that this works really good if you get it up to 90 degrees. You don't want to get it up past that because that can burn you pretty bad. So get it up, zap it up to a higher temperature. By the way, side note, you can heat oil in the microwave oven. I wouldn't have students do this if it was impossible to heat oil. You may have heard by reading important things on the internet that you can only heat water in the microwave oven. In fact, I've come across a lot of scientists who believe that the only way heating happens in a microwave is that water is heated. Well, that's not the case, because by IR we've demonstrated that there is no water peak in these oils. If there's no water, then you can't be heating the water with the microwave. It can't be working that way. So that's baloney. And if you think about it, this should be kind of intuitive. How many of you have enjoyed microwave oven popcorn? Right, raise your hand, you've all done it. Okay. How does that work? Do you have a little bit of water sprinkled inside on each little individual pop? No, nobody does that. But no, because they're dry.
Inside there's no water?
They have very little water, not nearly enough to cause the explosion. So the real source of the heat is the interaction of the microwave radiation with the oil. You can heat oil using microwave energy. So just saying, that's what I'm excited. All right. So then you put the plunger into the syringe. You got that hot oil. You just hulk out on that baby. And if you've done this, you know what I'm talking about. It's really, really hard. You basically have to be Andrew in order to get it to work. Great forearm strength on that guy. So you crush it in there, and it comes out this beautiful golden oil, which is mostly coconut oil or macadamia nut oil, and some of the nutmeg butter. There's actually oil in the nutmeg, and those molecules that cause the trace. So then you throw away the plug of used nutmeg powder, and then you add the coconut oil or the macadamia nut oil. It depends on which one you heat in the microwave. The total has to be 15 grams because we make a certain, and then you got to heat this up again. We make a certain amount of sodium hydroxide solution, so you have to get up to 15 grams in order to take the capacity of all that sodium hydroxide. This is very simply done, again, without using electricity, except to run the balance. And you got to stir it because sodium hydroxide pellets will stick like epoxy glue to glass if you just kind of swirl it around. Yeah, Spencer has experienced that. So make sure you stir it. It also makes the pellets dissolve more quickly if you do that. It'll evolve some heat, so don't hold the beaker on the bottom because you'll burn your hand. It evolves heat as it dissolves, which is kind of unusual. And stir that in. Then you just add that solution to the oil. And with about 5 minutes of stirring, you'll come to something that's much thicker in character. You can, if you desire, pour that into a cute mold. And voila, after a day or so, it firms up into a cute piece of soap that you can present to your mother and say, this is what you get for $10,000 investment. And everybody's happy. I feel really good that I helped you to learn how to make something that you could give back to your family. And I get all the good feelings that should come to the professor for having done that work. So there's Macadacoconutmeg Soap. We have gone further from there, and the nature of research is that you're always trying to one-up yourself. Julian helped us this last year try to figure out if we could use butter to make soap. Julian succeeded. He did. He made soap straight from butter, adding nothing but sodium hydroxide and a little bit of water. But it doesn't smell very good. He found out that the extra stuff that comes along for the ride with the butter gives you different, we'll say, odors that are not all that pleasant. But he did discover that if you do a process that Indians have known about for centuries, called heat treatment of butter, you can precipitate out the sugars and the proteins and the salts that are naturally present in butter, and what you're left with is a golden oil called ghee. Now, if ghee is used as a substitute for oil in the same recipe that I talked about before, you can make a beautiful soap product that doesn't have that bad smell and has this just barely off-white beige color to it. Very, very different from most soaps. And it works. It lathers well, and it cleans, and he measured soap suds level to prove that it actually lathers well. So he accumulated sufficient failure in figuring out that butter's really not where we want to go with this project, but he also succeeded. So good job, Julian. Samantha took a different tack. Based on Brock Koppelman's work of juicing a piece of coconut and finding out by centrifugation that there's water and oil in that juice that comes out of the copra, the white stuff, not the milk that's inside the coconut. It's very different. That is a high concentration aqueous solution of proteins. And when you pick up a whole coconut and shake it, it's not the liquid inside your middle ear that's sloshing. It's the liquid inside the coconut, right? That coconut milk is different from coconut juice. So what Samantha did this last year was she took the coconut juice that Brock Koppelman showed had been made and used that as the starting material to make coconut soap without having to add anything else. Well, a little bit of water and a little bit of sodium hydroxide. Put it together, it made beautiful soap. It traced really, really well, probably because there are extra proteins in that mixture. And I think it's the proteins most likely that are causing the trace to happen fast. And got the soap, but the drawback is, well, it's a natural product. And there are odeurs that go along with that. And this one smells like fish in a dumpster in mid-July. Not your favorite odor. However, she took the lemons and made lemonade by realizing that if she washes her hand, interestingly enough, the bad fishy odor is very water soluble. So it washes away and you can't smell it anymore. And what's left, the residue that's left on your hand, smells just a little bit coconutty. Nice, light scent. So, yeah, she accumulated sufficient failure, but she also found the solution. See, back to that pun. The solution for the problem. So, kudos to Samantha. Good work. I'd like to briefly talk about my references. Susan Cavich's The Soap Maker's Companion. This lady actually took, can you believe this? Took general chemistry and organic chemistry just to write a good book, which became this book, right? Back in 1997, probably before you all were born. She was in class figuring this out, and she wrote a book on it. And I've got a copy up in my office, and I think there's one in the library. You can borrow it if you want to learn more about that. The green chemistry stuff comes from a book by Annie Stoss and Warner that's also in the library. And there's stuff on this all over the internet. These guys are really famous that came up with the green chemistry theory and practice. And my own lab has the most recent iteration of the changes we've made to the soap lab to produce green soap. Finally, I'd like to acknowledge student workers. Jesse Kramer worked on the nutmeg replacement. Nathan Ford made liquid oils easily available to us without electricity. Gillian Williams proved that butter soap was a bad idea, Dr. Baldwin, but someone had to do it, right? And he was a much better solution. And Sam found out that coconut soap, although it works, it has some odoriferous drawbacks. And then tons of students that have helped over the years actually proved that these soap recipes can be used and accomplished by students to make their moms happy. Thanks. Now, technically, we do have 5 minutes for questions. Are there any questions? I'm going to go with the student first, and I'll come back to you, Dr. Lee.
You said you wanted to avoid heat, right?
that requires electricity. Uh-huh.
So they're using it to cold process soap?
Well, that term is very misleading. Cold process just means not turn you into a crispy critter heat. It's not heating it to 200 degrees Fahrenheit. But you do have to use heat, even in the cold process soaps. They use heat about in the same range, somewhere between 60 degrees C and 90 degrees C. So we're not actually violating that principle. But if you really wanted to greenify this, maybe a project that you could help me with would be to not use added heat, just use the temperature of the environment. I think we would find that you're going to have to supply the energy somehow, and basically that's going to mean stirring it for a long time. I don't know if I can sell that process for anybody, but if green chemistry is a pure outcome that you want to make come about, maybe that's something to try. Okay, Dr. Bradovich.
If Sam's soap smelled like fish and the
Yes.
fishy thing is water soluble, could you do
Okay.
a water extraction of some sort to try and get rid of it?
Yeah, I mean, it could be as easy as those molecules have migrated to the surface of the soap piece. So if you baptize the soap a little bit, just take it out and shake off the water, maybe that smell will have gone away. Of course, it's also possible that the fishy smelling odoriferous molecule is intimately mixed throughout the entire body of the soap. In which case, you only really take care of it by using the soap. So, yeah, I don't think that would necessarily be as easy to do, but maybe. Are we good? Remember, you guys can always ask questions of the speaker. Never be intimidated by my years of soap making. I do some other things too, but I'm always happy to answer questions. All right, thank you for coming to Natural Science.